This sequence does not appear in OEIF yet. Okay, so now we define the corresponding quantities, F infinity and Fp. And as I said, we already know the asymptotic behavior of F infinity encodes the Riemann hypothesis. And that means the study should be done experimentally. Don't expect to prove anything. Okay, here's a plot. So now let's look at ord P of 2. You may compare this with the original plot, which had the stripes, okay, and was non-negative. But here, when you do it, the stripes have kind of gone away. This is obtained by a Mobius inversion from the G of n stuff. You still see there's blocks having to do with the powers of 2, and it does seem to be more positive than negative, but it still looks like there's a bunch of negative values. So one conjecture would be that ord 2 of f of n is positive infinitely often and is negative infinitely often. I don't know how to prove that. In fact, I sat on this stuff for years thinking I should be able to prove that, but I never could prove it. What you can prove for each p, though, is it's positive at least once and it's negative at least once. But you can prove that for every p. It appears to be infinitely many times, once on every power of p, actually. Okay, and perhaps the negative values occur a positive fraction of the time. You still have the big jump. You have a jump from 2 to the k minus 1 up to 2 to the k. And that, of course, you can prove because there's a huge bunch of 2's that come in the denominator of the Farey fraction when you go to the next level, and that produces the jump. So the jump is definitely there, but where the bottom of the jump is, we don't know for sure. The claim is the experimental evidence suggests the jump at the 2 to the k minus 1 always takes you from a negative value to a positive value. And if that were the case, then this function would grow like n log n. Cannot prove that. I can prove n log squared n, but then I can't locate that the jump is from negative to positive. But on every experimental test we've run for every prime power that's been tested, it always went from a negative value to a positive value, or possibly 0. So there's 2 zeros at the beginning of this. It's just to show you the size of the ord p at 2 to the r. Well, 2 to the r minus the third column is where it's located, the negative power, and then r times the column to the right will give you the positive power. I wanted to say, I have 2 slides here. Now let's ask about the Riemann hypothesis. The Riemann hypothesis is encoded in the F infinity of n. You have to subtract off a funny arithmetic term, which is the sum of the Euler phi function. That's already complicated. But once you subtract that off, you get the Riemann hypothesis in terms of the error term. And the thing I wanted to investigate particularly is there a version of the Riemann hypothesis visible at each individual prime p in studying ord p of fn? In order to do that, you have to subtract off a complicated arithmetic oscillatory thing as the main term, and then get the Riemann hypothesis encoded in the error term. And here's the answer. Yes, you can do it. Maybe. Maybe. Let's say the experiments suggest that we have a candidate for such a formula, but we don't have any sort of proof that's rigorous at this point that you can get an analytic number theory estimate that proves it. And due to time constraints, the details are omitted except for the final slide. Thank you.